Hello everyone. I'm gonna talk about gel electrophoresis. Myself, Nitish Kumar, from MSc third semester. My roll number is 19. So first we'll see about agarose gel. Agarose gel electrophoresis is a separation technique which separate the DNA on the gel based on the molecular weight. So what is an agarose? Agarose is a polysaccharide polymer material generally extracted from the seaweed, which is seen in the right side of the image. The genera Gelidium and Racillariae. So agarose is a linear polymer made up of a repeating unit of agrobiose, which is a disaccharide made up of D-galactose and 3,6 anhydro L-lactopyranose. So what is the principle is that of agarose gel electrophoresis is that to separate DNA using agarose gel electrophoresis, the DNA is loaded into a precast wells in the gel and a current applied. So the positive backbone of a DNA molecule is negatively charged. So therefore, when placed in an electric field, the DNA fragment will migrate to the positively charged anode. So the rate of migration of DNA through agarose gel is facilitated by the following factors such as size of the DNA molecule, agarose concentration, DNA conformation, voltage applied, presence of ethidium bromide, type of agarose, as well as electrophoresis buffer. If you take a size of a DNA, the velocity of the DNA fragments decrease as their length increase and is proportional to electric field. The speed of the DNA fragment movement is dependent on the length of the DNA. So the second one is agarose concentration. A linear DNA fragment of a given size migrate at different rates through gels containing different concentration of agarose. Then the DNA conformation. There are three conformations. One is supercoil, linear, and relaxed coil. So when you compare the three DNA conformation, the supercoil will be moving faster than the relaxed coil, and the mid one is a linear DNA. The fourth one we are going to talk about is voltage applied. As the voltage increases, the speed of the DNA also increases, but the voltage should be limited because it heats and finally causes cell to melt. To obtain a maximum resolution of DNA of less than 2 kb of size, agarose cells should run at more than 5 to 8 volt per centimeter. The fifth one is ethidium bromide, which is an integration of ethylene bromide cause a decrease in negative charge or double stranded DNA and increase in both stiffness and strength. So ideal ethylene bromide used in agarose gel electrophoresis is 0.5 microgram per ml. So the last two is a type of agarose. There are two major classes of agarose, or standard agarose and low melting temperature agarose, with gels at 35 degrees Celsius and melt at 65 degrees Celsius. So ideal agarose we are using in agarose electrophoresis is low melting temperature agarose. And the buffer, the most commonly used buffers are tris EDTA and tris borate EDTA. So we will move on to the procedure. First of all, we have to measure a 2 gram of agarose in 100 ml of TAE buffer. We'll make a 2% gel. Mix agarose powder in a required volume of 0.5 x GBE in a microwave for 1 to 3 minutes until the agarose is completely dissolved. Then let agarose solution cool down to about 50 degrees Celsius for 5 minutes. Then we have to add ethylene bromide to a final concentration of approximately 0.2 to 0.5 microgram per ml. Ethylene bromide binds to DNA and allows you to visualize the DNA under ultraviolet light. Once ethylene bromide is added to the sample, then we have to pour the agarose into the gel tray with a well comb in place. Let the agarose gel stand for room temperature for 20 to 30 minutes until it completely solidifies. Then fill gel box with 0.5x TBE until the gel is covered. So after that we have to load the buffer to each of your DNA sample. Carefully load your sample into the wells of the gel. Then run the gel at 80 to 150 volt until the dye lines approximately 75 to 80 degree of the way down to the gel. Then turn on the power and disconnect the electrodes from the power source, and then carefully remove the gel from the gel box. At last, then visualize the DNA using UV transilluminator. Next, we move on to polyacrylate gel electrophoresis. Polyacrylate gel gels are chemically cross-linked gels formed by the polymerization of acrylamide with the cross-linking agent, usually in methylethyl acrylamide. The most commonly used form of polyacrylate gel electrophoresis is sodium sulfate polyacrylate gel electrophoresis, that is SGS page, used mostly for the separation of protein. The principle of polyacrylate electrophoresis is that the technique is based on the principle that charged molecule will migrate in electric field towards an electrode with an opposite sign. So the protein molecule with the different shapes and sizes need to be denatured, and so that the protein loss is secondary or quaternary structure. Then the protein being covered with SDS are negatively charged, and when loaded onto gel and placed in the electric field, it will migrate towards the anode, and that's by a molecular sieve effect based on the size. What are the materials required? We need acrylamide solution, the resolvent stocking gel, isopropanol or distilled water, gel loading buffer, running buffer, staining, destaining solution, protein sample, the molecular weight markers, an electrophoresis chamber, glass plate, casting frame, casting strand, and combs. So the procedure. So we can divide the procedure in 3 steps. Like first one is a sample preparation, second one is a separating gel preparation, and the third one is a stacking gel preparation. First we'll see about the sample preparation, where the sample to analyze is mixed with HCl for proteins and urea for nucleic acid. So here for protein sample we have to mix with SDS, for nucleic acid we have to mix with urea. So then SDS in the, as I told you earlier, it's an anionic detergent that denatures the secondary non-disulfide linked tritary structure of a protein and additionally applies a negative charge to each protein in proportion to its mass. And a tracking dye, bromophenol blue, may be added to the solution. This typically has a higher electrophoretic mobility than analyte to allow the experiment to track the progress of the solution through the gel during the electrophoresis run. So if you see in the left side of the image, you can see the protein and the denatured part 4, which consists of trisacil, STS, tracking dye beta microethanol, bromophenol blue, glycerol, which gives the density to the protein, and double distilled water. Then we will see about the preparation of separating gel, which is 10%, and the pH of this separation gel is 8.8. We have to add water, acrylamide and bisacrylamide, trisacil, SGS. Trisacil should be 1.5 molar of pH 8.8. Then temmet and ammonium persulfate. So pour the gel, leaving approximately 2 cm below the bottom of the comb for the stacking gel. Make sure to remove bubbles. Then lay the top of the gel with isopropanol. You have to remove the bubbles at the top of the gel and also keep the polymerized gel from drying out. Then remove the isopropanol and wash off the remaining traces of isopropanol with distilled water. Once separated gel is get settled, then we have to prepare a stacking gel, which consists of water, acrylamide and bisacrylamide, trisacil, SGS, temp, and ammonium persulfate. The pH of the stacking gel is 6.5, 6.8, 6.5 to 6.8. So we have to pour the stacking gel on top of the separating gel and add combs to make wells. In approximately 30 minutes, the stacking gel should become completely polymerized. Clamp gel into a press and fill both buffer chamber with gel running buffer. So load samples and molecular mass of protein markers into the wells for separation of electrophoresis. There are separation of electrophoresis. Here electric field is applied across the gel, causing the negatively charged protein or nucleic acid to migrate across the gel away from the negative and towards the positive electrode. Depending on the size, each biomolecule moves differently through the gel matrix. Small molecule move easily fit through the pores of the gel, while the larger one have more difficulty. So then the detection. Following electrophoresis, the gel must be strained. For protein, most commonly use Comacin brilliant blue strain. And it can be visualized using autoradiography. And that's all about the electrophoresis. Thank you.